Mind for the window.
What?
You don't mind for the window, no?
No, I think it's a good idea to get some fresh air. So this is my last lecture of this intersection course, and I'm still trying to explain the Qaisar classification, at least some idea of it. And it's based on Qaisar dimension. So I'll remind you of Qaisar dimension. Minus infinity is the starting point. And that means that there are no sections at all in any power of a canonical bundle. So from the point of view of the canonical bundle, the worst possible thing. Qaisar dimension 0 is also looks rather bad, but the dimension of this thing is at most 1. This is for all n. Is at most 1, and for some n, it is 1. So this thing is not true. And then Qaisar dimension 1 means that the algebraic dimension of the canonical bundle is 1. So there are at least two sections here which are different, and you construct a meromorphic function. And 2 means the algebraic dimension with respect to the canonical bundle. It's 2. Okay, that's the thing. And I try to give a little idea of minus infinity. What you got here, you got ruled surfaces. So you get curves which are P1 bundles over curves. Any curve. In particular, you get Jacobs surfaces, which are the P1 bundles over P1. The rational surfaces, rational ruled surfaces. By the way, the classification is always for minimal x. That means you can't blow down to its manifold. Non-trivially blow down to manifold. You can blow down to a singularity maybe, but not to a manifold. Well, it came up. And in particular, the rational P1 bundles, which are called principal surfaces sigma n. They're interesting. And then I talked to you about Hopf surfaces. This is C2 minus 0 modulo contraction mapping. And it could be a linear contraction, and this could be linear as yesterday, or a polynomial one in the classification, which is well known, nowadays well known. So these things of the old work of Latif, I don't know how to pronounce it, Latif or Latif or what, I think it's French. And there's a modern paper on these contractions, in case you're interested in the dynamics. of a very nice younger French mathematician named Fabre. There are many people working in this area, but Fabre is one I like very much. And there are other and there are others, other interesting types of surfaces. And one of the modern authorities using really interesting vector bundle methods here is Telemann, maybe one N, I'm not sure. I suppose this is a common Romanian name, I don't know, is it? Telemann? It's German, I don't know. Anyway, it's Romanian.
There is a street in my town called like that.
Hmm?
There is a street in my town called like that.
In your town called Telemann, but maybe it's named after him, he's a good mathematician. Also, he has relatives who are well-known physicists. It's an interesting family.
I think it's an Armenian name.
Armenian name. Anyway, he grew up in Romania, was educated. Very interesting. He's in France. So this is not complete, so there are many things here that are open and very interesting types of things. For example, earlier I should mention names in a way. For example, Nakashima. There are many people in Japan who are specialists in this area. It's very, very interesting classification of these things. These are highly non-algebraic surfaces. Okay. These things here, and up here, of course, these are algebraic. So, in codiver dimension 0, of course, tori are here, and that's an interesting subject, and I recommend, if you're interested in this, to see books of Mumford. Mumford's elementary books. I mentioned this morning. Very, very good. And the surfaces which have been studied very intensely, also recently for reasons of connection to both string theory and mirror-symmetry, are so-called K3 surfaces. And these K3 surfaces, there's a beautiful article, again by Beauville, on K3 surfaces. It really is the fundamentals of K3. He actually is, I forgot, Beauville directed a seminar in France. It's quite typical. They have a seminar on the subject. You lecture today, you lecture tomorrow, and so on, and they went through the whole thing. So there are many authors. But I think the guy who was really directing this thing is Beauville. If you're ever interested, ask me, I'll find it for you. It's also an asterisk. So what are K3 surfaces? Well, K3 surfaces, we assume that the canonical bundle is trivial. I should mention in brackets here, there's surfaces called Enriquez surfaces, which are closely related by a 2-to-1 covering, where the second power of the canonical bundle is trivial. And the difference is a 2-to-1 covering. But let's stick with this and the first Betty number to 0. As I said this morning, this implies, with some serious work, that the fundamental group is so simply connected. Now, what I said this morning, I just will repeat. These are parameterized with additional structure. Additional structure by a 20-dimensional family, 20-dimensional space, parameterized by a 20-dimensional space. they are in general not algebraic. Not all algebraic. I guess there's a dense set of algebraic surfaces, but they're not all algebraic, and quite often they don't have any meromorphic functions whatsoever. So that's a very interesting thing. And let me tell you the additional structure. What we talked about this morning. I thought it was worthwhile seeing that. The idea is of the additional structure is this in one dimension. And then we'll generalize it to higher dimensions. So you should know this in one dimension. And for sure, and then higher dimensions is interesting also. If you take a Riemann surface, genus 2 for example, then of course you have basis of the fundamental group, maybe this, I don't know, I draw them not at different base points, maybe it's bad to do that, I don't know. You have 4 generators of the fundamental group. And you choose these generators, which quite often are called A1, A2 of one type and B1, B2 of the other type, say these sort of standard generators of the fundamental group. Well, maybe of the homology. Now, as you notice, these are curves in middle dimension. So it's a curve. This is dimension 2 as a Riemannian manifold. So the dimension over this thing of R is 2. And these curves, I don't know, A1, A2, and so on, dimension is 1. The deep observation is 1 is half of 2. So it's middle dimension. And that means that if you take 2 curves in general position, because it's middle dimension, they will intersect in points. Right? And so you have the intersection pairing here, and
So the curves are not one codimension?
curves are one codimension. Did I say it wrong? Curves are one codimension in the surface. Real curves are one codimension in this surface. Okay.
Yeah, but how can it be also half dimension? I mean, in this case it's half, but...
Yeah, I'm only talking about this case.
Oh, okay.
I'm doing didactics now. I wanted to motivate something by looking at something you understand, namely just the surface. Okay? And you see the intersection numbers. So A1 intersect A2 is 0. A1 intersect, you look down what the intersection numbers are. These things don't intersect. And now I'm going to write down an intersection matrix. And so you're interested in A1 intersect B1 and so on. So I think if you write down the intersection matrix, it will look something like this. And the reason is if you change the order here, you will really change the orientation of the curve and you can get a negative intersection number. You know that. I mean, you just see what it means, when one curve crosses the other, how it looks. And if you change the order of the curves, you call this the first curve and this the second curve, then we get a plus number, +1. If you call this the first curve and this the second curve, you get -1. So what you get here is a Z module or a vector space, a lattice with an intersection pairing. So what you get is a lattice here. This is lattice H1 X Z or H homology X Z. It's the same with an intersection pair. Okay. Okay. So a marked Riemann surface in the sense of Teichmann. I'm not not sure how, I don't know his work, of course, but I know the answer. So a marked Riemann surface in this sense is the surface X with a marking, and a marking is an isomorphism from H1 XZ to a fixed lattice. Okay, the fixed lattice is, in this case, Z4 equipped with this intersection pairing. Okay? This is of course, this is not positive definite. Okay? So a marking is, a marked Riemann surface is that. Okay? It is the surface itself, is a complex manifold, with a choice of an isomorphism to a fixed lattice. Now this is abstract and so on, and now we have an isomorphism to a fixed lattice. Okay. And in the classical Teichmüller theory, for example, then the Teichmüller space, so the space of all such things, the space of all such things for the genus fixed, of course, it's fixed because you want to have a fixed isomorphism. This is called Teichmüller space, genus G. And what you have done here is, this is some space, by the way, it has a natural complex structure. It is of complex dimension 3G minus 3, and this is realizable as a domain in a natural way in C 3G minus 3. And it's even contractible domain. It's just contractible as a set of cell. So it's some trivial thing in some sense. Okay. Now, a point in here is a marked Riemann surface. And what you would like to do is say, here's a Riemann surface with a marking. You might have the same Riemann surface but a different marking. The point is, a priori, it's not so clear you can parameterize Riemann surfaces, but it is clear you can parameterize Riemann surfaces with a marking. Okay? So you will have all these different Riemann surfaces with different, same Riemann surface with different markings, and now you want to look at this domain, let's call it this Teichmüller space. You would like to look at this Teichmüller space modulo the equivalence relation, so that the same Riemann surface with two different markings is defined to be equivalent. Right? This is mod out this by the equivalence relation. Okay? You're lucky. You're very lucky. This equivalence relation is given by what is called, what is it called?
So it's
Well, it's given
what,
by
mapping class group.
Huh?
The mapping class?
Yeah, it's given by the mapping class group. So there's the mapping class group here, it doesn't matter, I'll call it the mapping class group, that gives this quotient. So let me call it something like lambda G, gives this quotient, and then the true space that parameterizes Riemann surface is Teichmüller space modulo the mapping class group. This is an interesting space. Actually, the Teichmüller space, and from this point of view, is not so interesting. And this space is fantastic. This thing is a compact complex space, by the way, with very well-known compactifications, with many beautiful things known about it. So, I mean, somehow the Teichmüller space is just a cell. It has very interesting metrics on it, all sorts of interesting things. But from this point of view, the interesting space that parameterizes every Riemann surface of genus G is what we call MG. The space of all Riemann surfaces of genus G is really the one way of looking at it is Teichmüller space modulo that. So when you hear Teichmüller space, people going blah blah Teichmüller space, that's what it is, and that's how it arises. Okay. The reason I said that is that K3 surfaces can be parameterized in the same way. So the only difference is that so the same analogous discussion for K3 surfaces. Well, in the case of Riemann surface, the relevant topological thing is H1. Here, the relevant topological vector space, or we consider H2, and it doesn't matter cohomology or homology. I will do it in cohomology. H2Z equipped with intersection theory. Okay, that is the additional structure. H2Z equipped with this intersection. So this thing will be isomorphic if it's a K3 surface to a certain lattice. Okay, just as this one was isomorphic to a certain lattice with this quadratic form, intersection pairing. Now I have to tell you what the intersection pairing is. The signature is of signature 319. So, and if you're interested at all what this is, this lattice has a name. You take 3 copies of a hyperbolic plane and 2 copies of what is called E8. And you see E8 is 8, 2 times 8 is 16, 3 times 2 is 6, 16 plus 6 is 22. So this is 22. The hyperbolic space has 1 plus space and 1 minus space. That's its signature. So you get 3 pluses here. This thing is negative definite. So an E8, each node of E8 is minus 2. That's the, well, I could make E8, so minus 2. So anyway, the lattice is very well known. It is of signature 319, and that's it. So, so a marked K3 surface X is a K3 surface with an isomorphism phi to the fixed lattice of signature 319, which is really 3 times the hyperbolic plane plus 2 times this lattice E8. It's a very well-known arithmetic thing, I think. Okay, that's the kind of thing that's very well known in arithmetic. You know? Okay,
Oh, you mean the lattice? Or?
No, this one, particularly this one.
Okay.
Okay, so this is a set of marked K3 surface. Okay, and you can do the same thing. This thing is, there's something like the Teichmann space. So this thing, I like very much calling this D+. This is, the reason I call it D+, is I realize it, as I said to you this morning, is a certain positive domain in a certain quadric. This is a 20-dimensional domain. It is not contractible, as is Teichmann space. And that's very good that it's not contractible. We like that. And this is good. But this is not the parameter space for K3 surfaces. The parameter space is here you have a K3 surface and a marking. Here you have another K3 surface and a marking. Alright, so there are too many, they appear too many times. So you have the same idea if you're talking over somebody. You want to mod out with the markings. And so, you have the idea, go kill the markings. Well, in other words, 2 things are equivalent when the K3 is the same, but the markings are not good. Well, in this case, the group that identifies these markings is very well understood. This group here that acts, so that I call it over there letter G, this group here that acts is SO 319Z. Okay, so what you're dealing with here is the analogon of the Teichmann space modulo this group. Okay, and then you learn very quickly this is horrible. It is not Hausdorff quotient topology. It is the worst thing you can think of. Okay? So this is very bad quotient. Okay? And therefore, you really never make that quotient formally. You really stay in this analogous place to the Teichmüller space, carrying the marking along with it. This is what you need to learn in general mathematics, in general, trying to parameterize things. You almost never can do it. You have, in order to get things done, you usually have to add more information and parameterize more things, and then somehow that separates across. The bad stuff gets separated out, and that's it. So this is an example of K3 surfaces. Now, maybe I will give you two examples of K3 surfaces. Concrete. Okay, you will like this. So, concrete examples. So the two standard methods that I will explain. The first method is due to Kummer. So, and certainly strongly influenced by Weierstrass. So Kummer surfaces. Okay? But what is a Kummer surface? So let's recall, before doing a Kummer surface, Weierstrass's idea. If you have a torus of one dimension, C modulo a lattice, then you have a quotient of this torus by plus minus the identity. Right. This realizes the torus as a 2-to-1 ramified cover, ramified at 4 points over P1. This is P1. This is P1. This is the torus. Right. You even know exactly where the ramification points are. If this is the lattice, the ramification points are here, 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 here. So that's really great. This thing, in the analytic sense, is well known. It's the Weierstrass P function. That's what it is, this map. So, but actually it's just the quotient. Well, Kummer and Weierstrass were hanging out in Berlin, and so they talked to each other. Weierstrass is probably by that time involved in the administration of Berlin. He became rector. I don't know the detail. So, Kummer's idea is to take, the idea is the same idea. Take a two-dimensional torus. There's a two-dimensional torus. And now you go over and make something, let's call this thing down here X. X, which is the two-dimensional torus modulo plus minus the identity. All right? I mean, in other words, an element of the torus is identified with minus an element of the torus. A well-known equivalence relation plus in the group. The group element is identified with its inverse. Okay? Well, you have this quotient. Kummer is very happy with this quotient. This is very good. This is a ramified quotient. It's the same picture, except that everything's two-dimensional. Unfortunately, it's ramified, I don't know, at 16 points. No, yeah, it's, how many points? 16? 16 points, did I say? Why did I say 16? Half lattice points. How many are there? Can you count? You're good at counting. Half.
Yeah, 2 to the 4.
2 to the 4 is 16 points. Right? Yeah? Okay, so it's ramified at these points. And we get a quotient. X. These points here, however, are singular. This thing is over here, the point, even though it's a ramified quotient, these things are smooth. These points are singular, however, the singularities are not too bad. So the singular points are cone singularities. They are simply cone singularities, which you can think of as cone over smooth conic. in P2. So put this thing in, put a conic, smooth conic in P2, go to P3, look at the coma where there it is. That's the singularity. So these singularities are not bad, and everybody knows how to blow them up. So you blow these things up, and you got a smooth surface, and this surface is K3 surface. Okay. It's called a Kummer surface. The beautiful thing is, in this parameter space over here, they're dense. So you can make many arguments about general K3 surface by saying, okay, nearby is always, arbitrarily nearby is a Kummer surface. It's very nice. No.
No.
Well, these are algebraic if and only if the torus. Many things you can just relate back to the torus. The tori are generally not algebraic, but it's a torus, so you have a lot of hands-on information about Kummer surfaces. Okay, so look, that's a good class of students.
I mean, what happens if you take a different, instead of dividing, okay, so plus minus identity is the only finite group that you can divide.
No, you can, it's very interesting to take other finite groups and to see what you get, because you're going to get other things. Okay. That is, these are in dimension 2, classified by a very good friend of mine in Fujiki. So it's a very nice article, and one of the big article, young in his career, in the Kyoto Journal, you know, the big Kyoto Journal. Classify finite groups acting on tori and their quotients. So two-dimensional tori.
So in one dimension?
One dimension is not difficult. Okay. You see, one dimension, one dimension, it's not difficult, just a little, remember the thing, you have the moduli space, and the fundamental region here, right? And you have this tau, and this tau. This is I, and this is something like 60 degrees. These two taus have exceptional automorphism. Otherwise, it's just z goes to minus z.
I see, so in those cases,
yeah, and you want to do something analogous in higher dimensions, and it's not possible. It's really non-trivial.
Okay.
It's very interesting. In dimension 3, for example, even in dimension 2, it's very interesting. Fujiki's argument is somehow, for me, very deep. So, finite groups in dimension 2 are classified by Akira Fujiki. Well, that's one way to make these K3 surfaces, and one way to make things in general, so I thought I would tell you about it. So in other words, mod out by a finite group. That's what you're saying, mod out by some finite group, see what you get. I mean, that's a heck of a good method. Yeah, but you have to get the finite group acting in the first place. On tori, of course, it's very easy, right? Because you just look at linear stuff. And that's interesting. Yeah, thanks for the question. So the second method, and this last method general method I would like to propose in this discussion is an absolutely fundamental method in algebraic geometry. This is called the adjunction formula. It's a principle. Adjunction is somehow a principle, but I'll call it a formula now. So the background hope is this. For example, in our context here, let Y be a surface, a smooth surface, in P3. See? Okay. I mean, P3C is a place you can go to, and if you're not stupid, you're looking for things. The first place you're going to look is P3. You might want to look in a torus, but then you're causing yourself trouble because it's much more difficult. So you look at P3, so that means that Y is the zero set of a homogeneous polynomial of 4 variables. Of degree D. So we say Y is of degree D. Well, okay. So Y is a surface. So the hope is that you can say this implies that the codirative, that Y is something that you can understand in the Codira classification. Something concrete, let me write it, is concrete someplace by Codira, in Codira's list. Right? You would like to know, you hand me a homogeneous polynomial, for example, Fermat polynomial, right? Maybe you say, okay, let me see here. Here's a good one. And you ask yourself, what's that surface? Right? It's a reasonable question. So how does it fit in this Codira classification? Experts say, well, that's a K3 surface. And the way to see that that's a K3 surface is by something called adjunction formula. And I'm not going to explain the adjunction formula. Okay? So this is, for example, let me just say that this is a K3. So this adjunction formula is a very simple situation. You have a complex manifold X and a complex submanifold Y. Okay? And you have an exact sequence. You have the tangent bundle of Y, I mean the homomorphic tangent bundle here. You have the tangent bundle of X restricted to Y. And you have, this is an exact sequence along Y, so we write this is the normal bundle of Y and X. We sometimes write it this way. It's completely clear. You have the tangent bundle of Y. Here's Y. And you have the tangent space of Y, but that's much smaller, so instead you think of it embedded. This is tangent space, this thing here, of Y. And then the whole thing here is the tangent space of X restricted to Y. And the quotient vector bundle, of course, there's no canonical complement unless you choose a metric with orthogonal complement, but the quotient is the normal bundle. Okay. Now, you can see that when you've got this thing set up, you have a block form matrix for the transition function. This is the transition matrices Fij for the tangent bundle here. Why is that? Because we have a distinguished two-dimensional, a block, I don't know, it depends how big this block is, that's determined by this thing. See, if you didn't have anything distinguished in this, you wouldn't know how to simplify this matrix. But if you have a distinguished subspace here, you then have the transition function looks like this. Transition matrices look like this. You don't have a complement, and that means that you have both of these blocks here, right? So then the normal bundle thing for this thing, well, you mod out. So what you really have is just this piece here, right? Because you modded out the rest. You modded out the first subspace. So you killed this part of it. Okay? So what this says is, well, that's what it says. But then what you do here is you go to the determinant bundles of these things. Well, okay, so the determinant bundle means you take the top wedge product of this, you get the determinant of that. So you get the determinant bundle of the tangent bundle of y, okay, times the determinant bundle of the normal bundle of y in x. The product of these determinants, the product of this determinant with this determinant equals this determinant. That gives you the determinant bundle of the tangent bundle of x restricted to y. And if you check it, this is the same thing as the determinant of the tangent bundle of x restricted to y. This is rather good. What I did here is I took determinants, so I get line bundles. These are all line bundles, right? These are the transition matrix of that guy is here, the determinant of that guy. Transition of this guy is here, the determinant of that guy. These are all one by one matrices because it's top width product. Okay? That's a silly thing, but very deep. Okay. Now let's write this in my language of this morning. This is the canonical bundle of y. Anti-canonical bundle of y. Right, because it's the tangent bundle, not cotangent bundle. Whatever this is, I don't know. This is the anti-canonical bundle of x restricted to y. So this is a beautiful thing, except for this mistake that we have to understand. You can compare the canonical or anti-canonical bundle of this guy with the canonical and anti-canonical bundle of that guy. So if you're here in P3 and you have something like this, you can compare the canonical bundles here if you have some information. So that's the way you compare that is called the adjunction formula. We have the advantage of bundles and all of this, so this you will deem this as being trivial when you see what I say about it, but I think we have the advantage of modern concepts. Max Noether understood this in some sense, but when you read Max Noether, you don't believe he understood it. It looks complicated. So let's look at that again. So let me transform this. So now let's say that y is smooth. So y is smooth. Assume that. X, of course, is also smooth. X and y are smooth. And let's assume y is a hypersurface. So that means codimension is 1. You see, I'm assuming that exactly the same situation we have here. If this is a surface, this is a two-dimensional submanifold of P3. Okay. So let's look at this in the codimension 1 case, where life will be much easier. Okay, so I'm going to write the formula down. I'm going to twist it around. Well, I'm going to write it down. Here's the anti-canonical bundle of y times this mysterious determinant bundle of the normal bundle of y and x equals the anti-canonical bundle of x restricted to y. Okay? That times this tensor product. That's too much. Let me see here what I want to do. I want to just take inverse of all this. So it says that I don't know what I want to do. So if I take inverse of this, what I get? Canonical bundle of y time equals the canonical bundle of x restricted to y. I inverted that, so I get inverse here, and then I bring this over here. I hope I don't make a mistake. The inverse of the normal bundle. No, no inverse, right?
No,
Hmm?
there is no.
Right?
Ah, yeah.
Okay. I want to check that I haven't made a sign mistake, so I have to use my is that really right? So that times that equals that, and that is correct if the canonical bundle is. So let me just check for fun what I get here. This would be in case of, by the way, I'm going to do, I know in the background what should be going on. This should be H4. And now if I have, for example, let's do it in P2. So this would be H3, and suppose I have y of degree 3, so the canonical bundle is trivial. So that this would be determinant bundle of the normal bundle of this thing. So that would be, that has to kill this 3. What am I talking about? This is minus 3, yes, this is minus 3, and then this should be plus 3, and that's correct, I hope. Okay, I'm a little bit worried that I missed a sign someplace here. Now, here's y, and y is given locally on ui by fi equals 0. And these things will define, they're compatible. So fi equals fij fj. Okay? And the fij's are then see, I'm a little bit worried I'm going to make a sign mistake here. The fij's are the transition functions, define a bundle, define the bundle of this y as a divisor. So I don't know how you, oy. So, or the line bundle ly. Okay, right? So, okay. Now look what happens. dfi, now you're going to help me argue. dfi is equal to fij dfj, right, on y. You see, if you differentiate this thing here, you get another term, but on y, that thing is 0, so that vanishes. So you see the differentials of these things, this thing defines the same bundle. Yeah, these differentials define the same bundle. So this bundle, restricted, defines the same bundle. Okay, so what are these differentials? The differentials of this, so this is hypersurface H, and defined by a function f equals 0. And now the kernel of f, df, is the tangent space, right? So this is the tangent space of this well, this is y. This is the tangent space of y. Okay? So if I've got this right, this thing's going to span the normal direction. And I'm worried I've got the wrong, I mean, I know, I may have made a sign mistake here someplace, but I know what the formal, I mean, you see, what is this df? Somehow it looks to me, what does this look like? What is this df? Right? What is df? It defines, what is this df? Its kernel is the tangent space. So it looks to me like it spans the dual bundle of the normal bundle. Doesn't it look that way to you? It looks that way. It looks that way to me too. And I mean, okay. It looks to me like this thing spans. You could regard this as spanning the dual space to the normal bundle, right? Oh yes, of course. Of course, it is a frame it is a frame at each point for this dual bundle. It is, okay? It is a frame for the dual bundle. And the frame transforms in the opposite way the sections transform. So this, you should think of this as a frame for this thing, the dual bundle. And it transforms this way. Yes. Right. And however, the transformation, you know, for a line bundle, if you write down a line bundle and you write it down locally as a divisor, you write it down this way, right? SI equals Fij Sj. And the frame will be, if these are the frames, the frame will transform in the opposite way. Right? And so you see it's double gemoupled here. So this is a frame for the dual bundle. So therefore the sections transform of the dual bundle transform I don't know. Let me try to say it again. The frame for the dual bundle. Okay. No. The frame and the sections transform the same way. The coordinate transforms opposite. Okay, so this is a frame for the dual bundle. I'm confused. Okay, this frame, for sure, this is a frame for the dual bundle. Right? This is a frame for the dual bundle. Right. So a frame for the bundle would be this, not the dual bundle. So this, I was right what I said. This is a frame for the dual bundle. This is a frame for n. So in our system of writing down the bundle, the transition functions, this is a frame, so the transition functions are Fij. So there's double dual. Okay. So what am I saying here? Okay. All I'm saying is that this bundle here is the defining bundle for y in F. So let me just write this L of y. The defining bundle of y in F. You understand? I got mixed up between frame and transition for the frame and transition for the sections themselves. Yeah, okay, that's great. Now watch. So, here we go. Canonical bundle of y. So let's let y be in projective space. Canonical bundle of y equals canonical bundle of projective space restricted to y. Tensor the bundle of y. And now, what is the bundle of y? Y is given by a homogeneous polynomial of degree d. Okay. And that is the generating bundle for linear polynomials, which we call the hyperplane bundle, to the d power. Okay. But I missed, to the d power. Okay. So that's the sections of h are the linear sections, the sections of h squared, the quadratic polynomials, section h cubic polynomials, and so on. So in this case, I need to compute that, and the calculation is easy. It's h to the minus 4. So what we have here is h to the minus 4 times h to the d restricted to y. So that says this is h to the d minus 4 restricted to y. And you ask yourself, when is that a K3 surface? The question is, when is the canonical bundle trivial? And it's when the degree is 4. Okay? The typical calculation. So degree 4, you see, the canonical bundle has to be trivial. You use a junction formula. You do a computation what the canonical bundle of P3 is. It's the canonical bundle is minus 4. surface of degree D is a polynomial of homogeneous polynomial of degree D. It's a section of this bundle. So you get D minus 4 here. So D equals 4, if and only if Y is a K3 surface. So you see a huge number of K3 surfaces here. By the way, you see, if you do it right, modulo automorphisms, a 19-dimensional family. And so you're not seeing them all, you're seeing a very interesting family here. So those are two ways of getting K3 surfaces. Adjunction formula, that's a really easy way to do it. You just add this formula. Maybe you don't want to prove it like I do, but that's the proof. And what was the other way? Kummer surface. So those are really interesting ways of getting K3 surface. Well, I have a few minutes to complete the classification.
So here I have a question. So I mean, if you look at functions like zi over zj, I mean, if you look at z1 over z0 or z2 over z0 and so on, I mean there are homomorphic functions, right?
Right. Yeah.
And I think the transcendental degree is more than, I mean, it's probably 2.
Of what?
Of the...
On the restriction of those functions to the surface.
Right, okay, I see, but that's...
yeah.
Oh, okay, so but the... Okay. So
very good. You take, those are two independent meromorphic functions. Right. For example, z1 over z0, right. Z2 over z0. Right. Restrict, those are...
Okay, but but they do not arrive at the... In this field that you define. I mean, you define this field C of X. I mean, they don't quite...
they most certainly do in some sense. Oh, I see they're not arising in the canonical...
The canonical...
no.
Okay, because here is...
No, because they are restrictions. See what they are. You're restricting the hyperplane bundle, the linear hyperplane bundle, to the K3 surface.
Right.
So that's some other bundle.
Right. Right, so it's not...
Okay? But, I mean, the way of thinking is good.
So, but then, I see. Because he also said that if you have something projective, then projective is...
I'm listening.
And he said that the case that the Qaisar dimension is 2 is basically... so anything projective has Qaisar dimension?
No. Everything projective has algebraic dimension 2. It is.
I see.
It has 2 independent meromorphic functions, but Qaisar dimension 2 means you pull those functions out of the canonical bundle.
Okay. Yeah. Okay.
Here you're not going to pull much at all out of the canonical. You're not going to pull anything out of the canonical bundle. Canonical bundle is trivial.
Right.
Okay. You might try. What you would do, you computed the canonical bundle. And you restrict it to this guy, but you get nothing, right? So there you are.
Right, okay.
You can restrict all sorts of other bundles and you get a lot of stuff,
right,
but it'll never be the canonical bundle. Okay. Let me just close these lectures by 2 or 3 remarks, and then we're finished. We go celebrate Alice's examination. So, for Qaisar dimension 0, I told you, very interesting. I hope you found this interesting. Tori and K3, and some others. But these others are rather special and, in my mind, rather easy to understand. So I won't deal with it. Qaisar dimension minus 1. I will very quickly say what Qaisar implies. It is not equivalent to X is an elliptic surface. Okay, let me just put it this way. S possesses an elliptic fibration and what that means is it's a fibration over a base, which is a curve, and the general fiber is a one-dimensional torus. One-dimensional torus. are special ones that have been classified by Qaisar. I think this is one of the big hard pieces of work of Qaisar. So Qaisar really explicitly, e.g., for example, what Qaisar did is he classified the singular fibers. So there are many fibers, and maybe here they will degenerate to something like this, or maybe they will generate to something like this. All sorts of possible degenerations of the fibers. See, you come together with all sorts of singularities. And there's a huge table of these things. These things turn out to be very interesting, even from the point of view of differentiable and topological format. So there's an entire book written by a topologist by the name of Friedman, who's a very serious topologist, on exactly the differentiable topology in the background of all these circuits. This is a fundamental thing. So that's Qaisar dimension 1. And then finally Qaisar dimension 2. So I remind you what Kayvon was just talking about. This means you have two independent meromorphic functions coming from the canonical bundle. Okay? There are many algebraic surfaces, but this is a special meromorphic function. And please notice if D, if say X is in P3 as a surface, a smooth surface in P3, and it's of degree D, then D bigger than or equal to 5 implies that the Qaisar dimension is 2. Look, you see it. If D goes to 5, this goes to 1. This is a restriction of, it's what you wanted to do. It's a restriction of these hyperplanes. So you have a huge number of these restrictions where you compute meromorphic functions. So for big D, these things are all general type. And this justifies the word notation. The notation, which is Qaisar dimension 2, we say the surface is of general type. Okay, because you see, a high enough degree, every surface is of general type. It's very interesting. Okay. So I'd like to mention, just to close, there's a lot of modern research on trying to understand these things and their families and create new ones, and given a couple of invariants, try to create things with those invariants. There's a nice idea, a simple idea that you can have fun with even, because you can understand it very easily. And it requires some interesting modern research. So this goes back to the idea of Catanese. And right now there's joint work of Ingrid Bauer and Catanese on this idea of how to create things of general type, not just the surface of a high degree and something interesting. The idea is very remarkably simple. So let C1 and C2 be smooth Riemann surfaces. Compact Riemann surfaces. Simple-minded thing like this. Okay, and let gamma be a finite group of holomorphic transformations acting on both. So a product of two things, the simplest thing you can think of. Okay? Let me just tell you, Felix Klein loved the following group. The group gamma of simple group of order 168. This is a beautiful group, by the way you know it. It is GL2 of F2.
No, F7.
F2. GL3 of F2, and it's SL2 of F7. That's what you started to say. But the easy way to think of it is the 3 by 3 matrices with entries in Z2. It's computer science. Right? Right? I mean, yes. This is a beautiful, simple group. And you can find beautiful curves here where this thing acts on both curves. And then what you do is look at X as C1 cross C2 modulo this action on both curves, this diagonal action. So let me just say, G of X1, X2 is just G of X1, G of X2. Now there are all sorts of things that go wrong here, but this is a great way of producing interesting surfaces of general type. By the way, now, it's a great problem of computer science, because in order to compute these invariants that are coming up here, even for rather small groups, it's a huge data problem.
Is it possible to classify these groups? I mean, to do these surfaces, or like depending on?
No, that's really what they're trying to do. That's the reason I brought it up. And let me just say that there are. So let me just say, there are regions. If you write down here C2 and here C1, there's some region in here. Or C1 squared probably. Some reason in here where all inequalities that you can find allow surfaces of general type. Okay, there's some. This is called the Miyayoka-Bogomolov, I think Bogomolov-Miyayoka line. There's some inequality here. This is here. This is this, and this and this. And now you have all the integral points in here. Yeah, and I give you an integral point, maybe near the line. It's your job to create that surface. It's allowed by all sorts of things that, restrictions on the invariant. And the idea of Fabrizio, Catanese, Andrade, and so on, and now really pushed by the two of them, is to do these diagonal quotients by finite things. Of course, you get singularities, you have to desingularize, you have to compute. And as I said, this has become a big computer problem. And they're finding new surfaces all the time, but in reality with computer. Okay, it's interesting. Yeah, computing the invariants, because God only knows, you might get some completely absurd thing. You have to compute the invariants, and that's related to the singularities you get with fixed points. Okay, so that kind of gives you an overview of the subject. It's a rather active subject still, particularly in surfaces of general type. And K3 surfaces because of the connection to physics. Okay. I would say three-folds is more active than the present. 3 dimensions is more. Maybe, I'm not sure. Okay, that's it. Thanks for coming. Thanks you guys for coming, and Kayvon for coming, and Qaisar for coming. Thanks to people who look at these videos.